Okay, so here we go. So last time we were talking about linear approximations, and recall we kind of adapted the idea of linear approximation from single variable calculus to a multivariable context, and we found that this formula satisfies the sort of analogous, sort of expected rules, namely it agrees with f in value and it agrees with f in, well, all of the partial derivatives. So it seems like a reasonable analog to our single variable idea of linear approximation. And then I introduced a notational convenience, this right here, which allows me to turn this great big long clunky formula into this much more compact formula right here. Okay, and this is about where we left off. Right. So for the moment, just keep in mind the gradient, this thing right here, is just a notational convenience for the moment. We're going to find later on it's actually very useful for other things. It's, believe it or not, it's geometrically natural in addition to being algebraically convenient. That's going to be a twist coming up. Okay, so a quick example. I'll zoom back in. Here we go. So looking at this function right here, how would I form a linear approximation to that function at this point, 1, 2, in this domain? All right, now the short version of the answer is we're going to just straight up plug and chug into that formula, and this is going to transform into the answer that you can see I already have written down here. So let's just take this one little bit at a time. First, I've got to compute the value of the function. Now, specifically at the point 1, 2. So you take 1, 2, you plug it into f, and what you find is it turns out to be 5. That's a little arithmetic, easy for y'all to confirm that. So again, plugging and chugging, nothing really exciting happening here. Next, now we're going to need the gradient. Okay, well, the gradient is the vector of partial derivatives, previously introduced. Right, so we take the partial derivatives. Now, y'all can do partial derivatives. Give it a quick look. Make sure you're good with these being the partial derivatives. Don't forget when you're taking a partial derivative, the other variable is a constant. Right, and that's why there's only one term in each of these partials. Okay. Okay, but now specifically, what we need here is not the gradient as a function, but the gradient evaluated at the point A. So again, I've got to take the formulas for the gradient. I've got to plug in A, and plugging that in, I get that vector right there. Ready? Good? Just plugging and chugging. Notice, right? Lastly, we have this x minus a thing, and let's see here, x minus a. Well, of course, I mean a we've been talking about. There's a, and you can see that right there. There's the 1, 2 being subtracted. And, of course, x is just the vector x, y. And so x minus a is really easy to write down. It's just, boom, it's just this. And done. There's our linear approximation. Now, if you want, you could take this linear approximation and kind of multiply it out and collect terms, move things around and rewrite it like this. I'm not really clear what's to be gained from that, frankly. And the example I can think of where this might be useful to actually simplify it is if you were going to code this into a computer and it was going to do billions of calculations and you want to speed things along, I guess you could, right? But it really, I think there's arguably more to be, more useful information visible. I can see what the gradient is in this earlier formation of the linear approximation, right? I can see explicitly where the base point is, right? And I don't know, it just doesn't seem to me like it's worth much to multiply that out. It's kind of subjective, I suppose, but anyway, don't just reflexively multiply things out. It's not always clear that multiplying things out actually improves and simplifies things. Okay. All right. Now, reminder, this formula that we just got through using, that formula is for real valued functions, right? So only for real valued functions. So the output is just a single coordinate. What if you have a vector valued function? Okay, well, I could, but I don't want to. But I could write down, again, a great, big, huge formula that satisfies certain properties. And then, just like I did here, I could introduce a notational convenience that allows me to write it more compactly. We could totally do that. It's just that great, big, huge formula is really big and really inconvenient, and I don't want to. And I don't think there's anything to be gained from that. So I'm going to introduce the notational shorthand first. So why are we writing down this thing here? What's the motivation for this? Well, it's going to be exactly the thing that will allow me to write my answer to my question in a convenient way. That's all it is. So it's still just a notational shorthand. You just are going to have to, not see it coming in advance, why it's convenient. So, all right, so this is called the DF matrix, and I'll say more about why it's called that in a minute. Notice that it's made up of partial derivatives. Notice that every one of the partial derivatives in this first column is a partial with respect to x1. How about that? Right? And likewise, if you were to continue the pattern in the second column, they would all be partials with respect to x2, et cetera, et cetera. The last column, they are all partials with respect to xn. So as a terminological convenience, I will refer to this first column as the x1 column, because that is the input variable that all of the elements of that column sort of have in common. Alrighty, likewise the x2 column, et cetera, et cetera. Okay, now let's take a glance at this first row. Bunch of different partial derivatives, but notice they are all partials of f1. These elements, they have in common not what you're taking the partial with respect to, but they have in common what you're taking the partial of. Right? So likewise, it makes sense to refer to this row analogously, and I think it makes sense to call this the F1 row. That makes sense? It's just terminology. Yeah.
What is F1?
So keep in mind this is a vector valued function, right? So the function f has m different output coordinates.
Okay.
Right? And they're called F1 through Fm. Yeah. Is that cool? Yeah. All right. Okay, so with that notational convenience set up, how do we do linear approximations? Here it is. And again, it's going to be an exercise I'm going to leave for you all to confirm that it does what it's supposed to do. But here's the formula. This right here, you can see it makes use, very powerful use, of the DF matrix that we just got through defining. And I assert, and y'all will confirm for yourselves, that this formula agrees with F in value and in all of its partial derivatives. L and F have all of the same partial derivatives. That is, L and F, all of the output components, they're partials with respect to all of the input components, are all the same. In other words, said differently, this I'm going to abuse the term linear. It's not actually linear, right? There's a constant term here. You're not allowed to have one of those if the function's going to be linear. But aside from that constant, what's left over is, in fact, linear. Of functions of this form, this is exactly the only one that will agree with f in value and in all the partial derivatives at the point A. Okay. Now, the way I want you to confirm this, I I don't suggest that you do this, in general for all values of, no matter how many different inputs, no matter how many different outputs. It would just be notationally clunky, and you can get the big idea by just picking some reasonable small values. So I would encourage you, for example, to let f have 3 input variables and 2 output variables. I think it'd be a nice, for example. And for such a function, write down exactly what df is, multiply out this, matrix times vector. You'll have 6 different terms, and then confirm that all this works. All right, and of course, if you get stuck or you're not sure or blah, blah, feel free to come to office hours. Happy to help. Office hours, the other instructor's office hours, help room. You got various different resources. Okay. All right, so example, and again, this is a lot like the example on the previous page. This is just a vector-valued example. Notice this function has 3 outputs. Therefore, there are 3 output coordinates. That's why there are 3 rows in this matrix. Right? Notice that there are 2 inputs. That's why there are 2 columns in this matrix. And each element is the corresponding partial derivative. So, for example, the x partials of those 3 functions are all there. Right? And the y partials of these 3 functions are all there. Is that cool? All right. So now, of course, we're going to need to know not just the derivative matrix in general, but I need to know what happens when you evaluate the derivative matrix at the point we're interested in. In other words, at 1, 2. So I'm going to plug in 1, 2, and plugging into those formulas, this becomes that. Everybody okay? Everybody happy? Okay. All right. All righty. Moving along. Quick observations. And these are just notice kind of things. The first column, we've already noticed that all of the partials were with respect to x1. This is a slight tweak of that already existing operation. I've observed that all of the individual elements are partials with respect to x1. Let me point out further, though. It's all of the partials with respect to x1 of all of the different coordinates of f. So, in fact, that first column, I can say, each individual element is a partial of a component of f, but the column as a whole is the x1 partial of the entire vector-valued function f. So, not a big observation, but nevertheless, it's a point of view. Now, another observation. Let's go back up here to our formula for f, for df. Here it is. Now let's look at this first row. We've already observed that every element is a partial of f1, but taking it just a little step further, not only is every element of this row a partial of f1, this row itself is literally all of the partials of f1. And we've already created a name and notation, etc., for where you take all of the different partials of a real valued function. That's a gradient, right? So this first row is the gradient of f1. Let's see here. There we go. Gradient of f1. And then likewise for the other rows, the gradients of the other component functions. Okay, so neat little connections between various different objects. Moving along. Okay, now y'all remember tangent lines, I'm sure. I want to review some old stuff. Let's see, let me zoom in. Here we go. Some old stuff. I hope y'all already know everything on this page. I suspect based on experience, that a lot of y'all have been allowed to kind of be sloppy with the terminology on some of this, and I know I've been, careful and uptight about the terminology on this before, but I think it's worth reminding you. This thing here is called the linear approximation. A lot of people mistakenly call it the tangent line. That's not correct. This is not a line. This is a function. This is an algebraic object, right? The tangent line is what you get when you take the graph of that linear approximation function. So again, it's in a Calc 1 context that would be reasonable to be viewed as a fussy distinction, but in this context it really is going to matter because not every picture we're going to draw is going to be a graph. And so at this point we have to be careful to distinguish a tangent line from a linear approximation. One is the graph of the other. Okay. All right, so now keeping in mind that this function f, the whole point of the linear approximation is to kind of mimic f. So if L is mimicking f, then the graph of f should be tracked reasonably well by the graph of L, namely the tangent line. So thus the name tangent line, it should kind of follow along with that purple graph. Does that seem plausible to everybody? All right, now with that recalled, let's make the analogous extension to a multivariable version. I guess I have to zoom out. There we go. So again, linear approximation. Right? Function, algebraic object. But we can talk about the graph of that linear approximation, and that graph I'm going to call the tangent plane. And again, the reason why, if I were to look at the graph of f, and if I were to compare the graph of f with the graph of L, the whole point of L is that L is supposed to mimic f. And if L is doing a really good job of mimicking f, then the graph of L should be tracking the graph of f. And thus this plane that we get when we write down z equals all of this stuff, the equation of the plane, should be tangent to the graph of f itself. Yep?
Is that tangent plane just expanding out infinity?
Yeah, that's right. When we draw these things, I don't have an infinite screen, so right. But yeah, so there's all sorts of sort of little cheap conventions when I draw things. My cheap convention is that most of the time, if I'm going to draw a plane, I will represent that plane by imagining a rectangle sitting inside of the plane, and it just makes it a little easier to. Otherwise, I don't know what else to draw. Right? Yes. Yeah, that's right. It's tangent specifically at, for this input value, which means it's tangent. The geometric tangency is happening at that corresponding point on the graph. Yeah, totally. And same question. Okay, yeah, cool. Everybody happy? All right. Okay, so now begins an awkward conversation. This is 2 pages of notes in which I'm going to cover what I would like to spend a week on. If it was, if time was not a factor, and if I really wanted to give you a thorough discussion of everything. Math219 is just not as rigorous as would justify spending that much time on this material. So if this were Math222, I would absolutely spend a week on this. Right? But that's just not what this course is. This is, a little bit more practical, I guess you could say. But nevertheless, I can't just not talk about this. This is really important. The idea of differentiability is a big deal. If you're not careful with the idea of differentiability, you will get hilariously wrong answers, dramatically crash and burn wrong answers if you're not careful about differentiability. right? So we do have to talk about it, but I'm going to do more sort of, here's a couple of examples of the kinds of problems that we need to be worried about, and then I'm going to pretty quickly go right to exactly the mathematical life hack workaround that makes all this go away. So here we go. I ask rhetorically, this formula that we wrote down a minute ago, is it really a linear approximation? Now, reminder, when I first started talking about linear approximations, right, we were writing stuff down, and I said, if it exists, and we have to assume that the linear approximation exists, because otherwise we have no sort of foot in the door. I can't talk about, for example, f prime unless I know that there is an f prime, right? What if the function's not differentiable, right? There's a problem there. So I didn't want to deal with the nasty questions. So I assumed that everything was nice, and then we could just make some algebraic observations about what behaves well. But now we have to actually address this question now. And how do I know that a linear approximation actually exists in the first place? In other words, how do I know that the formula that we wrote down will actually produce something that actually does a good job of estimating our function? And so here's what I'm worried about. This is what I'm going to call a counterexample. Here's a case where the formula we wrote down will fail terribly. Okay. Let's look at this function here. 2 input variables, 1 out. It's a weird function. It doesn't really have an algebraic kind of a formula. It has a rule of assignment, I guess you might call it, right, as we discussed earlier. But you give me an x and a y, and this will tell me whether or not the value of the function is either 1 or 0. And it's just kind of a strange function. But here we go. Let's draw the graph of this function. Sitting over the axes, where x is 0 or where y is 0, the value of the function is 1. And everywhere else, in other words, where neither x nor y is 0, in other words, not on either axis, the value of the function is 0. So in the whole first quadrant, in all the quadrants except for on the axes, in other words, the value of the function is 0. Everybody see what this looks like? Okay. All right. Now, I'm going to entertain the question of how I would do a linear approximation at the origin. And there is the origin right there. So now, of course, we have a formula for finding linear approximations. The formula says I need to, now at the point in question, I need to know what's the value of the function. Well, x and y are both 0, so the value of the function is 1. Now I need to know the partial derivatives. Keep in mind the partial derivatives make up the gradient. So let's start with, at this point, at the origin, of course. As I move in the x direction, how is the function changing? And well, if I'm on the origin, then I'm on the x-axis, and as I move in the x direction, I stay on the x-axis, and the function's not changing at all. The function is just not changing at all. It's always 1 as I move in the x direction. So the x partial is 0. Furthermore, now let's ask the question, what's the y partial? The y, again, at the origin. Here I am at the origin. As I move in the y direction, that takes me exactly along the y-axis, where, again, I just am following along like this. And that y partial 0, because the value of the function is not changing as I move in the y direction. Everybody okay so far? Doesn't seem to be a problem so far. I've got f, I've got the gradient. I can put them together with the formula on the previous page, and out comes this linear approximation. The linear approximation is just 1. And I am going to assert that this is unacceptably bad. This is not in any reasonable sense, an actual approximation of this function. Because consider the following. Let's look at what that looks like, and just for visual purposes, I'm going to kind of draw it like this. There it is, z equals 1. That's the graph of that linear approximation. Let's look at a particular curve. I'm going to think about this curve that starts over here and then approaches the origin. It never gets to the origin, but it approaches the origin, like that. And as I do that, what's the value of the function? Well, the value of the function, for all those points, the value of the function is 0, because I'm not on the axes. The value of the function is 0. F itself is 0 for that whole curve. But the linear approximation is 1 for that whole curve. Right, so how good of an approximation? As I approach the origin along this curve, right, you'd think that my approximation would be getting more and more and more accurate, but it's not. It's way, way off the whole way in, even as I'm super duper close to the origin. The approximation's just way off. So unacceptable. This is not a linear approximation. I followed the formula. It just didn't work. Everybody see why this stinks? This is a problem, right? Okay, now let's try to be precise about what we don't find acceptable about this. I'm going to describe this concept called error. Error is the difference between the value of the function and the value of our approximation. You can see our errors here. Our errors are these red lines here. All these errors are exactly 1. And so one complaint that I could make about this, what went wrong in this example up here is my errors didn't approach 0. I mean, error is supposed to approach 0. If something's good, error should approach 0, shouldn't it? So this seems like a reasonable first shot at describing, what the condition ought to be. Maybe I should say that a linear approximation is acceptable as long as error approaches 0. Certainly that would allow me to eliminate this massive failure. Maybe that'll do. Maybe that's good enough. And of course, y'all can read what I've already written here and know that is actually not good enough. This is the surprising thing. It's just not good enough to require that the error approaches 0. Now here's my counterexample, yet another counterexample. Let's think about this function right here. F of x equals 5x. Here's the graph. And let me make an obviously ridiculous attempt to form a linear approximation. Now I'm going to again say this is obviously ridiculous. Right? It would be silly to say that 3x is the linear approximation of 5x. Obviously wrong. 5x is the linear approximation of 5x. Right? So, but okay, let's try to, does this satisfy our rule? Is this eliminated by our new requirement that error needs to go to 0? Let's play the game and see. Here's the graph of our candidate linear approximation. The error is the difference. You can see the error right there. Actually, let me do this with the pencil so it'll be more visible. Here's our error right there. And as x approaches a, namely as x approaches 0, those errors get smaller and smaller and smaller and smaller. Those errors indeed do approach 0. So I'm not happy, right? I mean, the whole purpose of hopefully, optimistically requiring that, I need error to go to 0 is because I wanted that to be the good enough to tell me when I have an obviously bad linear approximation. But it didn't. This clearly bad attempt at linear approximation, it satisfies my naive rule. That means my naive rule is insufficient. It's not good enough. Okay, how are we doing? Is everybody on board with that? Okay. All right, so I'm going to take another attempt. I'm going to describe something called relative error. Relative error is not just about error. Error says how far off is the output value. Relative error says how much error is there per unit distance away from the input. All right, so if my base point is A and I'm at the point X, then this is how far I am away from my base point. And kind of stands to reason that the farther you are away in the domain, well, the further you could understandably be away in the target. Let's look at not just the error itself, but the error in proportion to the input separation. Something to try. Let's play with it. Let's see if it works. And now applying to our same previous example, so let's see here. I'll try to use the same colors. Here's our original function, 5x. There's the graph. Here is our candidate linear approximation, 3x. Again, ridiculous. We know that's wrong. We need to find a condition that will make this go away, because clearly this is not a good approximation. And let's look at relative error. Well, relative error, right? Error divided by x minus a. And you can crank that out. That's 2, which is not 0. So if I were to require that not error, but relative error. If I were to require relative error to go to 0, then this obviously bad linear approximation fails, as it should. And it turns out this is exactly what we need. This idea of relative error, this is what distinguishes a bad attempt from the correct attempt. And so here is the pithy summarizing statement. Vanishing relative error. I need my relative error to approach 0. Okay. Now, how do we write that down mathematically? All right. Well, there's some formalities that have to get written down here. In fact, let's see. Can I keep this on? Yeah, let's do it like this. Okay. So, relative error. There it is. Don't forget that error is true value minus estimated value. Don't forget that our estimated value is the linear approximation. So all of this great big expression over here on the right, and if you look in the book at the definition of differentiability, you're going to see this expression, or something very much like this expression here on the right. Great big monstrosity. Where did that come from? All that is just relative error. That's it. Right? And so the idea that they want the limit of this great big monstrosity to be 0, that's just saying vanishing relative error. That's all it is. So this is what how we distinguish a good linear approximation. So if this happens, if this relative error always approaches 0, then we say that is indeed a good linear approximation. That means that all the scary, nasty, weirdo stuff that I showed you one of the examples, but there's a million others, and there's actually one of the interesting things about, if we had a week to spend on this, right, is that there are many different ways in which a function can fail to behave like we would like it to. And sort of the classification of these various different failures is actually pretty interesting. But anyway, that's not what this class is. If this condition is satisfied, none of those bad things happen, and we use the word differentiable. to describe that function. So differentiable means that formula makes good linear approximations. In other words, differentiable means that the relative error goes to 0. So that's all it is. Now, here's the good news. Y'all aren't going to have to deal with this monstrosity. By the way, let's recognize a scary-looking expression to have to deal with. After all, there's a magnitude in the denominator. Oh, gosh, magnitudes are square roots. That's hard to work with. There's a magnitude in the numerator. Again, square roots, hard to work with. This is a nightmare of an expression. But that is part of the definition of differentiability. Okay. All right. So what's the workaround? Oh, I'm sorry, I got ahead of myself. Just a little bit of terminology. No big deal. We previously discussed that this error is the difference between the actual value of the function and the approximated value of the function. I'm going to point out here that a different way to think about this is that the error is the difference between the actual change in the function and the linear estimate of the change in the function. This is an important point of view because both of these are objects of interest. So how much the function actually changes between the point A and the point X, we're going to be referring to that here and there. The word we'll use is increment. And how much we estimated from our linear estimate, how much we estimated the change to be, that's called the differential. So another way to say it then is that a differential is a linear estimate of the increment. Just a different point of view. Okay. All right. How is everybody on board so far? Okay. Workaround. Surely we're not going to actually deal with that directly. And good news, we are not. We are going to need to be able to conclude that a function is differentiable. A lot of the theorems that we're going to be using for practical, get the job done kind of purposes require specifically that the function be differentiable. If we apply those formulas from the from the theorems that we're going to be using later on to functions that are not differentiable, we will get garbage answers. Our bridge will fall down, right? Not good. So differentiability is a really, really important idea. And here's the workaround. The workaround is called continuous differentiability, which sounds harder. Certainly, continuous differentiability is a stricter condition. Fewer functions are actually continuously differentiable. It's a harder condition to satisfy. This does not sound helpful. But even though it's harder to satisfy, it is much easier to check. All you have to do is take the partial derivatives of the function in question. That's easy. Partial derivatives are the world's easiest derivatives. Just write down the partials. Confirm that they exist. Right? You got to make sure that there's no zeros in your denominator or natural log of a negative number or something like that. Right? Just make sure that they exist, and then just make sure that they're continuous. And again, this I claim also pretty straightforward. Remember, we already know that huge numbers of functions are continuous. All polynomials, continuous. That's an old Calc 1 thing, right? We're not going to prove that, but I'm just asserting that that's true, and it's true, and this is a perfectly reasonable thing to assume. Polynomials are continuous. Exponentials are continuous. Logarithms are continuous wherever they're defined. Trig functions are continuous where they are defined. A lot of students raise their eyebrows when I say this. A lot of students think, hey, wait. Tangent has this massive discontinuity in it. It's not defined there. Wherever tangent is defined, it is continuous. Right, so practically every function that you can write down is continuous where it's defined. Yes?
There's such thing as,
if it can be not defined and
Yeah.
that doesn't count as not continuous, then can it be like the other way around? Like
So there are functions that are defined at certain points, but they're not continuous there. If a function is not defined, then it's not possible to be continuous. But conveniently, so what we're worried about is, might there be a function where the function is perfectly well defined and yet it's still not continuous? And that is what I'm saying. It will never happen in this large category of functions: polynomials, exponentials, logs, trigs, basically anything you can write down. If they're defined, they're continuous.
okay.
Does that make sense?
Yes.
Yeah. So, the number of functions where they're defined and yet we can't conclude continuity, it's a very, there's not really a lot of those functions. They're weirdo things that you've either never seen before or that are written down in weird ways, kind of like this thing here, like piecewise defined functions, like this kind of obviously hacky kind of stuff.
Okay.
That's all.
Okay.
Yeah.
Saying it would be like a line where it's like, at that point it's that value, and then below
Yeah.
to include that point.
Yeah,
they
stuff
have
like
the
that.
value, but it's like,
That's right.
Yeah.
That's right. Yeah, exactly. Yeah. So that's pretty easy to eyeball. Yeah. Uh-huh.
So like whenever a function's not defined, it's
Yeah, if it's not defined, it's definitely not continuous.
Oh, okay.
Yeah. But if it's not continuous, it might still be defined. There are such cases, but those are the weirdos, right? And what I'm saying, the big point, and what the point that is y'all's friend, is that practically every function you know how to write down, if it's defined, it's continuous. Yeah, that's what makes life good for us. Yeah. Okay. So back to continuous differentiability. So here we have a definition of continuously differentiable. You take partial derivatives, you confirm they exist, you confirm they're continuous. All that's easy. How does this help us decide if a function is differentiable? Well, big theorem here. The big theorem is that if a function is continuously differentiable, then it is also differentiable. And so this is the big life hack. This is, oh my God, such a huge workaround. You don't have to deal with the definition of differentiability. The definition of differentiability is a friggin' nightmare. No problem. You don't have to deal with it. Just check that your function is continuously differentiable. That's easy to do. Partial derivatives, eyeballs, nothing to it. Once you know it's continuously differentiable, you snap your fingers, ergo differentiable. All right, here's an example. Let's look at this function right here. There's a function. We want to know, is that function differentiable? Maybe you want to estimate the values of this function using a linear estimate, or maybe you want to compute a directional derivative, or maybe any of a number of other things that we might reasonably and practically, rubber meets the road, need to actually do. I need to turn the crank, solve some problems, let's say, with this function. Those theorems require differentiability. So how do I know that this function is differentiable? All righty. Well, all we do is I take the partial derivatives. The partials are clearly polynomials. That's easy. This function's a polynomial. Just think about what happens when you take a partial derivative of a polynomial. You're just going to get more polynomials. So they're polynomials. Polynomials are all continuous, right? That means that we have satisfied literally exactly the definition of continuous differentiability, because the partial derivatives are continuous. Again, that's the definition of continuous differentiability. Which tells me then that the function is differentiable. Everybody happy with all that? Nothing to it. No messing around with nasty definitions on the previous page. Very cool life hack. Okay. All right. All right, now I do want to point out one thing while we're here talking about this example. This argument that I've given here is pretty terse, right? But notice all of the critical ideas are represented on the page. This is a really big deal. Keep in mind this class, I've said it before, I'm going to say it again. It's not a class about answers, it's a class about ideas and reasoning, right? And so the fact that you come to the correct conclusion is not the point of this question, right? If this were an exam question, I'm not looking for a thumbs up, right? I'm looking for a complete mathematically valid argument. And there's a lot of little details in here that all really matter. So, for example, here's what I would imagine I've seen the equivalent of in many cases. Students just not mentioning this part. Now let me scratch that out and let me complain now about what the remaining words here are really pretty lacking. The remaining words say correctly that the partial derivatives are polynomials. That is true. The partial derivatives are polynomials. And then the student immediately concludes that the function is continuously differentiable. Here's the thing. If you look back up at the definition of continuously differentiable, it doesn't say anything about how that relates to partials being polynomials. It doesn't say the partials have to be polynomials. It says the partials have to other things. So the fact that the partials are polynomials skips over the huge point that we need specifically this continuity to make the connection to continuous differentiability. The continuity there is that's really important. There's like maybe 5 or 6 points in this argument, and that's one of the big ones, right? So when you're writing down your work on an exam, make sure to think it through carefully. Make sure that you actually write down all of what is actually important in the argument, because that's where the grading is going to be focusing on. Is did you hit all of the relevant points, and is your argument mathematically valid? Again, it's not a question of whether you write down true statements. Of course, they do have to be true statements, right? But you need for your true statements to connect to each other and to be, mathematically clear. Okay, so I hope that makes sense. All right. Last thing, probably, looking at the clock there. Quick little observation about, by the way, how are we on? Okay, it is what it is. Nice little convenience here. Another true fact, every differentiable function is continuous. You may recall there's a theorem that looks a lot like this in Calc 1. Every differentiable function is continuous. Not useful as written. As written, this is saying that if I go to the tremendous inconvenience of deciding if a function is differentiable, then I get to conclude something that I already probably could have figured out at a casual glance. And that's not helpful, right? But what we can do instead is write down the contrapositive. The contrapositive of P implies Q is not Q implies not P. This is logically equivalent. If a function is not continuous, then it's not differentiable. Now it's useful because sometimes, such as in the case of this function right here, whose graph we're looking at there, sometimes it's pretty easy to eyeball glance and see that a function's not continuous. And if you can glance and see a function's not continuous, then yes, indeed, you get to immediately conclude an answer to the differentiability question. That function is not differentiable. And so, answer. So, nice little tweak, and just another cool fact about that. Okay, so we have 16 seconds left. Let's call it a day. See y'all later. Have a good weekend, and we'll pick up here next time.